This is the last section of trig that we're going to work on, and it's called verifying trig identities. And really what it is we're going to be looking at a trig equation that we're not sure if it's actually a true equation or not. And so we're going to prove that it is true or not true. So something that you've got to pay attention to is this huge caution right here. This is not the same as solving equations, meaning you cannot apply the same calculation to both sides of these kind of equations because we aren't certain that they're true. We're trying to prove it. So you can't add the same number to both sides. You can't multiply the same value to both sides. Keep that in mind as we're working on these. First, we're going to take a look at some basic simplifying. This first problem, 1 over sine of alpha minus 1 minus 1 over sine of alpha plus 1 is really what we need to think about adding fractions. And in order to add fractions, you need to have a common denominator. Now, in the case of these two, these denominators look awfully similar, but they are not the same, so we cannot simply combine these. What you can do is to either find a common denominator, but in this case we won't be able to, or we can multiply each fraction by a version of 1 and create a common denominator. So what I will do is I will multiply this first fraction by this denominator here. Then I'll multiply this second fraction by this denominator here. And here's what that looks like. So I will multiply by the sine of alpha plus 1 over sine of alpha plus 1. And I'll multiply this one by sine of alpha minus 1 over sine of alpha minus 1. Multiplying these numerators is easy. I get sine of alpha plus 1. The other numerator, I'm going to put these parentheses because it's minus this whole thing. That numerator becomes sine of alpha minus 1. Multiplying the denominators is going to be a little bit trickier, so I'll do that off to the side here. And I'll FOIL. First times first gives me sine squared of alpha outside times outside, inside times inside. And the reason I'm doing those together is because this gives me minus sine of alpha, this gives me plus sine of alpha, which cancel. Then I'll do last times last, which will just be minus 1. Now, from our Pythagorean identities, we should know that all of this is equal to the cosine squared of alpha. So my denominator in all of this is cosine squared of alpha. Now I'll distribute this negative, and I end up with sine of alpha plus 1 minus sine of alpha plus 1. So here I have positive sine of alpha, negative sine of alpha. Those cancel. And then I have 1 plus 1, which is 2. So this gives me 2 over the cosine squared of alpha or 2 times the secant squared of alpha. The next one's not quite as hard. We're just squaring this one. So you can actually just use the rules of squaring. It would be a squared plus 2a times b plus b squared So a squared gives me sine squared. And then 2ab would be 2. A is sine of alpha. B is negative cosine of alpha. And then b squared would be cosine squared of alpha. Now on this, what we should notice is we have sine squared plus cosine squared. And from our Pythagorean identity, we know that that's equal to 1. So we end up with 1 minus 2 sine of alpha cosine of alpha. For this type of problem, my strong recommendation is that you replace the tangent of betas with something like x. Then you can rewrite this entire statement in terms of x, and it kind of helps you see what it is you're supposed to do. So I'll rewrite this as 4x squared plus x minus 3. And what I can see is that now I've got a quadratic. And quadratics we can deal with in a bunch of ways. This one is actually factorable. In case you forgot how to factor, you put your parentheses here, and you start off with what number can I put here and here will multiply to give me 4x squared, and I start very simply with 4x times x. Then I think about, well, what goes here and here that will multiply to give me negative 3? Well, I need a positive and a negative. I need a 3 and a 1. So then what I do is I see, does it work for my middle term? Meaning 4x times 1, negative 3 times x. Will those combine to give me plus x? Well, this is plus 4x minus 3x is equal to positive 1x, so that's correct. Now that I've done that hard part, I'll then rewrite this with tangent of beta in place of x. Taking a look at the next one, some things should stand out pretty quickly. The first is that cotangent times tangent is equal to 1. So when I rewrite this, I might start with in case you're not sure about why that is true, remember that cotangent is equal to 1 over tangent. So the tangent of alpha times 1 over the tangent of alpha is equal to just 1. From here, what I recommend in this case is to rewrite 1 over tangent squared as cotangent squared. Now I should be able to go to my Pythagorean identities and see that cotangent squared plus 1 is really equal to cosecant squared. Now those last 4 problems, we weren't even verifying anything. We were just going through the process of some simplification that you need to be familiar with in order to verify. When you are verifying, some tips. First of all, work with the more complicated side of the equal sign first. It doesn't matter if it's right or left. Look to see what's more complicated. Complicated means that there are pluses and minuses, rather than either fractions or multiplication. If you can, express things in terms of sine and cosine. Sometimes that actually makes it a lot simpler. Anything that's expanded, factor it. because again, if we can get those in terms of Pythagorean identities, we can substitute. And then when you're substituting, think about whatever side it is that you're not changing, because that's the goal that you're trying to aim for. And then finally, on page 649 in your textbook, there's actually a very comprehensive list of these tips. So here's the first equation that we're going to verify. Again, we're not saying that all of this is in fact equal to 1. What we're saying is we need to prove whether it is or is not. For this one, I would say let's get everything that we can in terms of sine and cosine. And the more complicated side in this case is this, because we know that 1 is pretty simple. So cotangent of x we could rewrite as the cosine of x divided by the sine of x. We're multiplying by sine of x. So to make things simpler on me, I will write this as the sine of x over 1. And then again, we're multiplying that by the secant of x. So when I rewrite that, that becomes 1 over the cosine of x. And I'm proving that that's equal to 1. Remember that when you multiply all your numerators and all your denominators. You can cancel anything that shows up in the numerator and denominator. We can do this because we are multiplying. If these were plus signs, we would not be able to do that. Remember that as you're working through these. So sine cancels, cosine cancels, and we are left with 1 is equal to 1, so this checks. This next problem is a little bit more difficult because we have things on both sides of the equal sign. But remember, we're working with the more complicated side, and our goal is to get to this value. So in starting with the more complicated side, I deal with this first. And one thing that you should absolutely notice is that inside these parentheses is a Pythagorean identity. So I will rewrite this to be the cotangent squared of theta times the secant squared of theta. Because remember, tangent squared of theta plus 1 is secant squared of theta. And I want to prove that that's equal to cosecant squared of theta. Now, I'm going to rewrite both of these in terms of sine and cosine. Cotangent squared becomes the cosine squared of theta over the sine squared of theta. And the secant squared of theta becomes 1 over the cosine squared of theta. And I'm still proving that that's equal to the cosecant squared of theta. Now, because I'm multiplying, I can cancel. And what happens when I do is that I'm left with 1 over sine squared of theta, proving that that's equal to the cosecant squared of theta, and we know that it is. So this verification checks. Some things that I want you to pay attention to, I kept theta in here the whole time. Don't get lazy and drop that. It is not appropriate. It's not correct if you drop the theta or the alpha or the x or whatever you're taking the cotangent squared of. Also notice that I kept this side the same the whole way. So I only worked on one side of this equation. Also notice that I did everything in a vertical fashion, meaning I started with something and then I wrote directly underneath it. I didn't move all over the page. These are things that I want you to do when you're working through these. These are things that I will look for. And then finally, I didn't end here. I took this and brought it down to exactly what it was I was trying to prove. So you should always have that something is equal to itself when you're working through these.